So now that we have some good justification about why we are allowed to pretend that du dx is a fraction and treat it that way, let's go ahead and do some substitutions here. We'll start with easy, work our way up to more complicated ones. So sine of 5x. This one you might be able to guess in your head without even doing any substitution at all, but let's follow good form here and try it. So you see that you've got an inside function, which makes you think of the chain rule, so that's a clue that we're going to do substitution. The inside function here is the thing inside of the sine, so that's 5x. So we can choose that to be our u. And then what is the du going to be there? Du over dx going to be there. That's going to be 5. So let's see if this has transformed into a nicer looking integral when we did this substitution. So now we get sine of u. We like that. But I cannot write a dx here because this is still single variable calculus. And just as with the optimization problems, we couldn't take derivatives of functions of multiple variables. We can't take integrals of functions of more than one variable either. So we have to figure out what dx equals in terms of our new variable. But that's what we can do down here. If du over dx is 5, and we do this crazy, but seemingly now legal thing about pretending that du dx is a fraction, I can solve for dx here, and I'll get 1/5 du equals dx. That's just by bringing the dx to the right side and dividing the 5 over to the left side. Meaning I can replace this dx by 1/5 du. And so now you want to ask, the normal thing to ask yourself in a question like this is, have I made the integral easier? And in this case, I think we have. So we can pull the 1/5 out front by one of our integral properties. And now we've got 1/5 sine of u. And do you know a function whose derivative is sine of u? Sure, it's negative cosine of u. And let's not forget the plus c. But just as the case was when we did the chain rule problems, we don't want to have a u in our answer because u was not part of the original function. So we replace the u by whatever it equaled. In this case, we're going to have negative 1/5 sine of 5x plus c. And we can check if this is the right answer. If we take the derivative of this, the derivative of negative sine, I guess not negative. Oh, I changed my sine to a cosine. That's the trouble there. That should be a cosine. Let's now try to take the derivative. See, this is good because this is a good thing for you to do. Check by taking the derivative to make sure you get what you started with. And if you don't, then you made a mistake, as I just did. If I have negative cosine, the derivative of negative cosine is positive sine. So I get positive sine of 5x, which is good. Chain rule says take the derivative of the inside, meaning multiply by 5. That cancels the 1/5, and we're left with sine of 5x, just like we're supposed to. Let's try another one here. What do you think the inside function is here that I should be letting u equal? We've got this e to the something, so that makes us think chain rule. So let's let u be 3x squared. So then what's du dx? Du dx is 6x. So what is this now going to become? We've got an e to the 3x squared. That's just going to become e to the u. We like that. But what's left over up here is this x dx. So can we figure out, according to this, what x dx equals? Sure. If I multiply the dx to this side and divide the 6 to the other side, we'll get 1/6 du equals x dx. Meaning I can replace that x dx by 1/6 du. Now we should stop and ask ourselves, have we made the integral easier? Definitely, right? This thing was not very nice looking. This is much nicer looking. We can pull the 1/6 out front, and we have the integral of e to the u. And that's a nice clean integral that we know how to do. So do we know a function whose derivative is e to the u? You bet, it's e to the u. So 1/6 e to the u plus c, and then we should not leave u in our answer. So 1/6 e to the 3x squared plus c. And if you take the derivative of that, you'll end up with exactly what you're supposed to have, x e to the 3x squared. This is the only really big technique of integration that we're going to learn this semester. When you take Calculus 2, you'll learn a couple more. In the old days, you might spend almost all of the time in Calculus 2 learning one technique after another, after another, after another. This was before the reform days, as we talked about in an earlier class. Now, instead of spending so much time on just this algebraic manipulation where it wasn't clear that people were really understanding the meaning behind it, we focus on a lot of more different context, as we keep saying, verbal, graphical, numerical, and algebraic. And I think that's better. What have we got for our inside function here? We've again got an e to the something, so we've got that cube root. So if u is the cube root of x, that's the same as saying u is x to the 1/3, right? So let's figure out what du dx is. That's 1/3 x to the negative 2/3. And we should be happy to see this x to the negative 2/3 because we've got an x to the 2/3 in the denominator. So this is a good clue that this is going to be the right substitution. So let's see what this is going to turn into. Let's hold off on these limits for a second. We're going to get an e to the u. That's what the numerator is. Now here I've got dx over x to the 2/3. If I can solve for dx over x to the 2/3 here, I'll know what this equals. So if I bring the dx to the right side, and I rewrite x to the negative 2/3 in the denominator, I need to move the 3 to that side, and I'll get 3 du. So I have to put a 3 du there. Now, a lot of people will just carelessly write 8 and 27 here. We should not do that. Because anybody looking at this integral alone will see 8 and 27 and assume that those are values not of x, but of u. But 8 and 27 are really values of x, not of u. So we need to figure out what they change to. So if x is 8, what is that in terms of u? Well, u is the cube root of 8. 8 to the 1/3, u is 2. So I need to change this x equals 8 to a 2 because now I want to have everything in terms of u. Same with the top. If x equals 27, then u is 27 to the 1/3. You can see why I chose these numbers. U is 3. So all this stuff is sort of just work off on the side, choosing our u, figuring out what du dx is, and then changing these limits of integration. So this is the difference with problem C. Part A and part B were just indefinite integrals. We didn't have any limits of integration. This is a definite integral, meaning the answer should be a number. So now we can pull the 3 out front and have the integral from 2 to 3 of e to the u. And again, we already know a function whose derivative is e to the u. That is e to the u. And then we do the fundamental theorem. Fundamental theorem says we find an antiderivative, plug in the top number minus the bottom number. So we'll get 3e to the 3 minus 3e to the 2. And you'll notice that we never needed to replace u by the x cubed as we did in these earlier problems because we took the trouble of changing these limits here from the x values of 8 and 27 to the u values of 2 and 3, and then we could plug 2 and 3 directly in for u. An alternative that you could do is sort of forget about the limits for a while, just find the antiderivative in terms of x. So you would end up with 3e to the u, change it into 3e to the cube root of x, and then plug in the 27 and the 8, and you'll get this same answer. If you prefer to do it that way, that's okay. But just be sure not to plug in x's for u's or u's for x's. That's the common mistake. So here we got another one. Take a second, pause the recording if you want, try to choose what your u should be. See if you can do the problem. It's not maybe quite as obvious what the u should be. But if we let u be ln of x, then what's du dx? 1 over x. And that's a good sign because we've got a 1 over x here. So what's this going to become now? The ln of x on the bottom is going to become a u. We need to figure out what dx over x is going to become. Well, we've almost got it perfectly here, right? This says that du is dx over x. I hope you're appreciating the beauty of Leibniz's notation here, that it's not really a fraction, but because of the clever way he did this, we can pretend like it's a fraction and everything works out great. You'll see this again in multivariable calculus. So this whole thing, dx over x, just becomes du. And now let's figure out what to do about the limits. If x equals e, what is u? ln of e, which is 1. The natural log of e is 1. And if x equals 8, u is ln of 8, which is nothing nice, so we'll just leave it as ln of 8. So we're going to now go from 1 to natural log of 8. And if you're bothered by writing this as du over u, you can just write it as 1 over u du, if that makes it easier for you to see what the antiderivative is going to be. So now you've got a nice, clean-looking function to integrate, right? This function was not so nice. This is almost as nice as they come. So we know a function whose derivative is 1 over u. That's ln of u. Do we need absolute values here? It won't hurt to put them in. We don't officially need them because 1 and ln of 8 are known to be positive numbers. So we don't have to put the absolute values in. If you want to put them in, nothing bad will happen. So from 1 to ln of 8. So we plug in the first one first, ln of 8 minus ln of 1. And we don't need to simplify as usual, but ln of 1 is just 0. So this is just ln of ln of 8. And as you saw in that applet, if we drew the graph of this function and looked at the area between e and 8, or we drew at the graph of this function and looked at the area between 1 and ln of 8, they would both work out to be this number. Same thing with the previous example, part C there. Let's try 2 more. So what should our u be here? Again, take a second and pause and see if you can make a good guess for what u should be. We've got something in the denominator. It's got an x to the 5th in it. And we've got an x to the 4th elsewhere in the problem, which is a good clue. Because if we consider this to be our inside function, then we've pretty much got its derivative somewhere else. So if we let u be 1 plus x to the 5th, then du dx is 5x to the 4th. And we like that because we've got a 3x to the 4th up there. We would really love it if we had a 5x to the 4th up there, but we can still deal with this. This 3 is a multiplying constant, so we can pull it out front according to one of our rules. This in the bottom is just going to become u. And then what's left over is an x to the 4th dx. So we can take our nice expression down here and solve for x to the 4th dx by dividing the 5 to that side, 1/5 du, and bringing the dx to this side, x to the 4th dx. Times, or rather, 1, and then all of it times 1/5 du. So this 1/5 is a constant. We can pull it out front. And then we've got the integral of 1 over u, which we've already seen how to do. So that's 3/5 ln u. Now in this case, we don't know if the u is positive or negative, so we do need those absolute values, plus c. And then we don't want to leave u in our answer, so we replace u by what it was, which was 1 plus x to the 5th plus c. So if you take the derivative of this somewhat messy function, you will get exactly that. But probably you might not have been able to guess. Like in the very first substitution example that we did, you could probably guess what the antiderivative was just using backwards chain rule. I don't know. It's hard for me to look at this and guess that that's the antiderivative. You might be better at it. This last example is almost exactly the same as that one, except one difference. What is the difference? We have an x to the 10th in the bottom instead of an x to the 5th. So let's see what happens here. So let's try the same method as before. U equals 1 plus x to the 10th. Then du dx is 10x to the 9th. Is that the du dx you were hoping for? In this case, the du was an x to the 4th, and x to the 4th was exactly what we were looking for to make cancel. Not here, right? It would be nice if we had an x to the 9th there. Then this would work. But it didn't work. So sometimes the first substitution you try does not work, and you need to go and try a different one. This is a way that integration is a lot different than differentiation. Differentiation, it's clear what rule you're supposed to use. Product rule, quotient rule, chain rule. Substitutions or integration in general, sometimes you don't even know what technique to use first of all. As we said, you'll learn more techniques next semester. And sometimes the first substitution you pick isn't the right one either. But this gives us a clue. We were disappointed when we got this x to the 9th because we hoped we would have gotten x to the what? X to the 4th. So if we want our u to have an x to the 4th, if we want our du, we were disappointed that du had x to the 9th. We wish du had x to the 4th. If we want du to have x to the 4th, you need to choose u to be x to what power? This is our clue. This substitution didn't work, but it leads us to the right one. We wish that du had an x to the 4th. That's only going to happen if we let u be x to the 5th. Now you might be saying, I don't see any x to the 5th anywhere in there. So let's just see, though, if this is going to work out or not. This at least will give us the sort of du that we're hoping for. Because now du dx is 5x to the 4th. So let's see what we can do with this. The 3 is a constant. We can pull it out front. We've got an x to the 4th dx. If we solve for this, x to the 4th dx is 1/5 du. So all of that stuff at the end is going to become a 1/5 du. Now we just have a 1 on the top of the fraction. And then we've got this, 1 plus x to the 10th. What is that in terms of our new u, which is x to the 5th? There is an x to the 5th hidden inside of that 1 plus x to the 10th because x to the 10th is x to the 5th squared, meaning this is just 1 plus u squared. So sometimes the u that you're going to choose is not obvious. It might seem like it's hidden in there, and you won't know until you try. But we like this because that should look familiar. We know a function whose derivative is 1 over 1 plus u squared. We can keep the 3 out front, pull the 1/5 out front. We get a 3/5 out front. And now we have the integral of 1 over 1 plus u squared du, which I hope looks familiar. That's arctangent, right? So this is 3/5 arctangent of u plus c. And all that remains is to go back to the original variable. So 3/5 arctangent, our u, the u that worked, not the u that didn't work, x to the 5th plus c. And if you take the derivative of that, you will end up with exactly what you wanted. So take a minute to compare these last two examples and see why each substitution was the appropriate one in each case. And then we have a check your understanding so that you can practice substitution on your own.